Today we're going to look at graphing linear inequalities. So let's get started. Before we start looking at two-variable linear inequalities, let's do a quick review of how we graphed one-variable linear equations and inequalities in one dimension. So here we have the equation x equal to 3. And if we were asked to graph this on a number line, we would color in a point at 3. Because our x variable has the value of 3. Now how about the inequality x greater than or equal to 3? We'd again put a closed circle at 3, indicating that 3 is included, and then we'd shade the region of the graph greater than 3. So that's all the numbers bigger or greater than 3 on this number line. So we have x greater than or equal to 3. We show the equal to with the closed circle, and then the greater than by shading in everything greater than 3. Now how about x less than 3? So again, we have the number 3, but in this case, we do not have equal to. So it's simply x less than 3. So we're going to indicate the value 3 with an open circle. And then this is x less than 3, so we're going to shade everything smaller or less than the value 3. For these two inequalities, we have a boundary at the number 3, and then we're going to shade one side or the other. Now let's review graphing linear equations. And today, all of our linear equations and inequalities, they're going to be written in slope-intercept form. And the great thing about inequalities is that those same tools and techniques we use to graph lines, we're also going to use to graph inequalities. So this equation is written in slope-intercept form. It's in y equal to mx plus b form. So m is our slope, and our slope is equal to 1/2. And b is our y-intercept. And our y-intercept is -4. Let's start with this y-intercept. Y-intercept of -4, that means we have the ordered pair 0, -4. So starting at the origin, we're going to be on this y-axis because it is the y-intercept. And we're going to go down to -4. This will be our starting point. And how we move is determined by the slope. So with a slope of 1/2, again, this is rise over run. So with a positive 1, that means we're going to go up 1. And then a positive 2 in the denominator means we're going to go to the right 2. So up 1 to the right 2. And we can repeat that, up 1 to the right 2. Now a slope of 1/2, that can also be written as -1 over -2. These are equivalent fractions. 1 over 2 is the same as -1 over -2. This is rise over run. So with a value of -1, that means we're going to go down 1. And to the left 2. The negative directions are down for rise and to the left for run. We'll go down 1 to the left 2. One more time, down 1 to the left 2. And then connecting our points, we have our line. And this line represents all the ordered pairs, all those x, y values, that when you plug them into this equation, you get a true statement. So for example, looks like the point 6, -1 is on this line. Let's verify that that point makes this equation true. So we have the ordered pair 6, -1. We're going to plug these x, y values into the equation. So y is -1 equal to 1/2 times x. X is 6 minus 4. This is negative 1 equal to 3 minus 4. Negative 1 equal to negative 1. That is a true statement. Again, this line represents all the ordered pairs that will make a true statement when you plug them into this equation. Now let's look at graphing linear inequalities. So in this example, instead of having the equation y equal to 1/2 x minus 4, we have the inequality y greater than or equal to 1/2 x minus 4. So to graph this inequality, the first thing I'm going to do is write this as an equation instead of as an inequality. So we have the equation y equal to 1/2 x minus 4. This is in slope-intercept form. We have a slope equal to 1/2 and a y-intercept of negative 4. Again, this is the same equation we just graphed. So let's go ahead and plot those same points we got previously. So we had a y-intercept of negative 4 and a slope of 1/2. Here are those same 5 points we plotted previously. Now let's connect these points and draw our line. In this case, we have y greater than or equal to. So since equal to is a possibility, we're going to have a solid line. And this solid line acts as a boundary to this inequality. And then we're going to shade one side of this boundary line. Well, which side do we shade? We determine that by testing a point on each side. So on this side, I'll pick the point 4, negative 4. And let's see if we plug these values into the inequality, do we get a true statement? So I'm going to test the point 4, negative 4. So we have negative 4 greater than or equal to 1/2 times x. X is 4 minus 4. So this is negative 4 greater than or equal to 2 minus 4. This is negative 4 greater than or equal to negative 2. That is not a true statement. Now let's pick a point on the other side of the line. I'll go ahead and pick the origin, 0, 0. So we have the point 0, 0, or y value is 0, greater than or equal to 1/2 times 0 minus 4. 0 greater than or equal to 0 minus 4. We get 0 greater than or equal to negative 4. And that's a true statement. So now we're going to shade the region above this boundary line, because the ordered pair 0, 0 gave us a true statement. So every point, every ordered pair in this region will result in a true statement if we plug it into this inequality. In this case, since it's greater than or equal to, every point on the boundary line will also result in a true statement. So you can pick any point up here. So let's try negative 10, 8. We'll test that point out. This is negative 10, 8. So we have a y value of 8 greater than or equal to 1/2 times x. That's a negative 10 minus 4. We have 8 greater than or equal to negative 5 minus 4. 8 greater than or equal to negative 9. And that's a true statement. So graphing linear inequalities. The first step, we're going to rewrite this inequality as an equation and then graph the equation. If the inequality has a less than or equal to sign or a greater than or equal to sign, the line is solid. If equality is possible, the line will be solid. So this is like when we were graphing something in one dimension and we had x greater than or equal to 3, we use that closed circle. The closed circle is the one-dimensional equivalent of a solid line in 2 dimensions. If the inequality has a less than sign or a greater than sign, so we do not have equality, then we're going to use a dashed line. So this is equivalent to if we had x greater than 3 in 1 dimension, we used an open circle. The open circle in 1 dimension becomes a dashed line in 2 dimensions. So once we have our line drawn, this boundary line now separates the graph into 2 regions. We need to test a point in each region. Now, one of those test points will give a true statement. We will shade the entire region containing that test point. And every point that is in that region is a solution to the inequality. Let's try another inequality. Here we have y greater than negative 2x. Our first 2 steps will be to write the inequality as an equation and then to graph that equation. So we have y equal to negative 2x. This is in slope-intercept form. So we have y equal to mx plus b. So in this case, our slope is equal to negative 2, and our y-intercept is equal to 0. So with a y-intercept of 0, we have the ordered pair 0, 0. So that is our origin, and that'll be our starting point for graphing this line. Then we have a slope of negative 2. So we can write this as negative 2 over 1. Again, this is rise over run. So a negative rise, that means we're going to go down 2. And then a positive 1, we're going to run to the right 1. So down 2 to the right 1. Down 2 to the right 1. Negative 2 can also be written as a positive 2 all over negative 1. These 2 fractions both simplify down to negative 2. These 3 numbers are the same. So we have a positive rise. That means we're going to go up 2. And then a negative run means we're going to go to the left 1. So up 2 to the left 1. Up 2 to the left 1. So now we have 5 points that are on this equation. And this equation represents the boundary of our inequality. So if the inequality has a less than or equal to or greater than or equal to sign, well, we don't have that. What we have is an inequality with a less than or greater than sign. We have a greater than sign. That means our line will be dashed. So we're going to connect these points with a dashed line. Doing a quick ops check of what we've done, we do have a negative slope, and our line goes down as we move from left to right. It's always a good idea to do some real quick checking of your work before moving on. And one quick one to check is the sign of the slope. A negative slope, our line goes downhill from left to right. So we now have a boundary line that separates the graph into 2 regions. Now we're going to test a point in each region. We're not going to test a point on the line. We test a point in each region. So I'll pick the point 2, 8 on this side of the line. And negative 6, 3 on the other side of the line. So we have 8 greater than negative 2 times 2. 8 greater than negative 4. That's a true statement. Now we have a true statement, so this one should be false, but we're going to check it anyway, just in case we did our arithmetic wrong. So here we have 3 greater than negative 2 times negative 6. This is 3 greater than 12. And that is a false statement. So the region containing the point 2, 8, this region needs to be shaded. And any point in this region, if we plug those x and y values into this inequality, we will get a true statement. A great way to learn is to practice on your own. We will discuss in a bit, but go ahead and pause your screen and do these 3 problems. For the first problem, the inequality was y greater than negative 1/3 x plus 3. So for the first step, we rewrote the inequality as an equation and then graphed that equation. So this equation is in slope-intercept form. So found the y-intercept and the slope, able to get some points and graph the line. Since this is a greater than and not a greater than or equal to, we used a dashed line to connect those points. This boundary line has now divided this graph into 2 regions. We're going to check a point in each region. I checked the point 0, 9 and the origin 0, 0. Whenever I'm able to, I will typically use this origin 0, 0 as a test point because it does make the arithmetic easier. Testing the point 0, 9, we did get a true statement with 9 greater than 3. And then with 0, 0, we got a false statement. 0 is not greater than 3. So the region with 0, 9 needs to be shaded. We'll do the same steps with this second problem. We're going to rewrite this inequality as an equation and then graph the equation. So this equation is in slope-intercept form. We were able to generate some points on this line and then connect those points with a solid line in this case because our inequality is a less than or equal to. So the points on the line will be included in this solution set. We now have our boundary line, and we're going to select a point on each side of this boundary line. I selected the origin again, 0, 0, and also the point 2, negative 7. Testing the point 2, negative 7, we did get a true statement. Testing 0, 0, we got a false statement. So we shaded the region with the point 2, negative 7. And then for the third problem, first step is to rewrite that inequality as an equation and then graph that line to generate our boundary line. This is a less than inequality, so we're using a dashed line to represent our boundary. The points on this line will not be a solution. And then checking points on either side of this boundary line. The point 4, 5 resulted in a false statement, while the origin 0, 0 was true. So we're going to shade this region containing the origin 0, 0. Drop any questions you have in the comments. Continue practicing graphing linear inequalities, and I'll see you in the next video.